So let's have one last quick note about solving equation AX is equal to B, and let's talk about what is the column space of A. So we said that when you have a matrix A that is in, let's say, matrices of size n times p, meaning that they have n rows and p columns, they are going to, you can consider them as acting from well, you need x to be in Rp, and the result is going to be some vector in Rn. Okay, so for any x in Rp, so let's say x is x1 up to xp, you compute a times x, and that's going to be a vector in Rn. So let's say z1 up to zn. Okay, so, and how can we view that? We've already seen that actually, if you say that, well, we said A has P columns, so I can say that that's going to be column A1, column A2, up to column AP. Okay, so that's my matrix A, and it's going to act on my vector x1 up to xp, and the result z1 up to zn is actually that linear combination given by x1 times column vector a1 plus x2 times column vector a2 and plus up to xp times column vector ap. Okay, each of these columns having n components because I've got n rows, so that's why the result is in Rn. Okay, more precisely, well, we said that these are linear combinations of the columns of A, and the set of all linear combinations of the columns of A, okay, that is going to be called the column space of A, right? We can write so that we will get used to this writing later on. It's going to be, this is the span of the vectors A1, A2, up to AP. Okay, so that's the column space of A, and all the linear combinations of those columns can be written as this matrix equation A times some x in Rp. Okay, so what does it mean? What is the implication of this ID when I want to solve something like AX is equal to some right-hand side B, so with the same dimensions, so B is in Rn, X is in Rp, and A is in the set of matrices n rows times P columns. Okay, so that means that I can solve this equation solvable if and only if B can be written as a linear combination of the columns of A. In other words, if B belongs to the column space of A, which can be usually written as col of A. Another denomination that I'm going to use, especially during second semester when we do some generalization of this ID, is the image of A, or the range of A. Okay, these are two synonyms, well, which have a broader sense. So the column space is specifically for matrices, but it really denotes the image of the mapping that I've created using matrix A. Okay, so this is solvable if and only if we're in the column space of A. So that let me take one a bit crooked example. So let me take this matrix 1, 2, 3, 1, 1, 1, 2, 3, 4. Okay, I've got, so we are in R3. All right, so it's going to act on X, Y, Z, and it's going to give you, B1, B2, B3, maybe notations. Okay. And so you know that this matrix vector multiplication is really X times 1, 2, 3 plus Y times 1, 1, 1 plus Z times 2, 3, 4. Okay, so I need to find out whether for any values b1, b2, b3, I can find x, y, z that doing this linear combination will give you this b1, b2, b3. So I need to know what or is the linear space, the vector space that is given by this linear combination. And maybe you've already spotted the problem that we're going to have. We are in R3, we have three vectors, but it happens that this third vector, maybe we could call that A3, A2, A1. This third vector is actually the sum of A1 plus A2. Okay, so all the linear combinations that I'm going to make with x, y, with those three columns, sorry, are just going to be linear combinations of a1 and a2, because that's just going to be, so if I write this as x times a1 plus y times a2 plus z times a3, this is really going to be x plus z times a1 plus y plus z times a3, as a3 is really given by a1 plus a2. So the linear combination of these columns are actually linear combinations of two vectors. So what are these? Well, you know that if we are in R3, so those two vectors, I have really no idea how I should represent that correctly. So let's say this is the 1, 1, 1 vector, the A2 vector, and the 1, 2, 3 vector would be somewhere around here, let's say, and all the linear combinations indicated by those two vectors is going to be a plane with those two direction vectors. Okay, so this plane going through 0, 0 can be represented as I can find the parametric equation of the plane. It's going to be x, y, z, or given exactly what we say, as well. Maybe x, y, z is not very, let's say b1, b2, b3 is going to be given by a parameter times the vector 1, 2, 3 plus a parameter times the vector 1, 1, 1. Okay, and anything that is not given like this, you won't be able to solve this equation. Okay, and just as a final reminder, remember how, so that's the parametric equation of my plane. If I want to find the Cartesian equation, I must find the normal vector to my plane. Normal vector, I just use my two vectors and make the vector product between those two, and actually I've already computed that, but you can do it on the file too. So that's -1 to -1. So the Cartesian equation of my plane is going to be -x plus 2y minus z is equal to 0, 0, because it has to go through the 0, 0, 0 point, because I know it's a vector space. Okay, so anything that doesn't comply with this equation, I won't be able to solve. Well, any triplets b1, b2, b3 that does not fit this equation won't get a solution to ax is equal to b. Okay, so column space, that's your first very important spaces, matrix spaces, that spaces, vector space related to matrix that we were going to see. Okay, very well. Thank you very much.